All right, folks. Well, welcome back, and I should start by just quickly saying congratulations. We've made it through the course. This will be the last lecture before you take the AP exam, and so congratulations. I wish this could have occurred under more auspicious circumstances, but so much is out of our control, and so. But I do want to congratulate you folks again. Like I had pointed out at the end of the morning lecture, this is not something that people undertake as something to do for fun, but people undertake as a means to pursue a more serious science career. And so I wish you folks, I think everyone will do well in their careers, in their science careers. You folks will do fantastic on the exam on Thursday. And like I said, we'll wrap up with chapter 10 here. I just want to quickly go. I'll try to make this lesson a little bit shorter, but I want to quickly wrap up with a few things that you'll need to know for the AP exam from chapter 10, basically introductory stuff here, and then we'll wrap it up and we'll continue with the chapter 10 material after the AP exam. There's just a few final things I want to highlight from the chapter 10 material. And then what we'll do is I want to talk a little bit about thermal chemistry in the after the AP exam, and we'll wrap up the year with the discussion of nuclear chemistry. We can get to that, and then we'll talk about exams and your grades at that point. Okay. So with that said, then let's go ahead and let's get started with it. Okay, so chapter 10, we finished up with basically a discussion of the interactions between, or the what makes an atom unique, the properties of an atom, what we can discern about the properties of atoms from the data that we can collect. Then we moved from there into the discussion of molecules, how atoms interact with one another in order to form these larger particles known as molecules or formula units when it comes to ionic compounds. And so steadily what we're doing is we're building up the particular substance that we're looking at. And so what we're going to do here in chapter 10 then is we're going to look at the interactions between different molecules. So we're not just talking about the interaction between the particles, especially the electrons and the neutrons in an atom. We're not just talking about the interactions between separate atoms to form these chemical bonds. We're now looking at what happens when you have multiple molecules, multiple larger particles interact with one another to form these different states, to form the solid state, the liquid state, and the gaseous state. I mean, the gas state, not so much, because as we learned back in chapter 5, when we talk about gases, we kind of ignore the attractions that those particles have for one another. And so we focus here on liquids and solids and the properties that liquids and solids possess. Okay, and so with that said, then let's quickly just talk about the differences in each state of matter. And we know then that we've already learned this, and I'm not going to go over this too much, but each state of matter has very different properties that we can discern on a macroscopic level. They have certain properties that we can discern because of the way that the particles behave at the microscopic level. And so, like I've been telling you up until this point, being able to make that connection between what we can observe on a macroscopic scale and what we can explain and how we can explain that behavior on a microscopic scale is absolutely important. Okay? And so what we will be doing here is we'll be talking about what are the what properties of a solid, the particles, what properties of the particles, what's going on at the molecular level that accounts then for the solids that we can observe. Okay? What's going on at the molecular level that accounts for the liquids, the liquid state that we can observe. Okay? And so, like I said, we're going to leave out the discussion of gases because really the attractions, these interactions that we talk about, though they do exist for gases, the gas particles, remember, they're moving so fast that these interactions, even though they are there, are negligible. Okay? They don't play a significant role in determining the attractions that the gas particles have for another. And so, again, like I said, what we deal with when we dealt with the ideal gas law, when we dealt with the gas laws back in chapter 5, the assumption we made then that the gas particles have no attractions for one another. There are these interactions do not exist. Okay? However, with liquids and solids, since they are at a lower temperature and therefore they're not moving, the particles are not moving as fast. The particles don't have as much kinetic energy. These interactions play a very critical role in determining the differences between a liquid and a solid. Okay? But the difference there is not that significant, folks. The difference there is not that significant. And so even though we present the liquid state as as an intermediary state between the gas and the solid, when we look at the thermodynamics of the liquid state, we actually see then that the liquid state is closer in its behavior to the solid than it is to a gas. Okay? And so one thermodynamic piece of thermodynamic data that we can use then is that we take a look at the heat of vaporization here, and then we compare it to the heat of fusion here. Okay? So both of those are the enthalpies related to this change in state, the state change. So remember, with state changes here, we don't get a change. The change in temperature. We don't get a change in temperature here because all that goes into rearranging the structure of the compound. And so if you notice here, if we have temperature and time, in case of temperature, we can also use energy here. But the idea then is that as we start to add in heat, okay, as we start to add in heat here, at this phase change here, so make sure you understand at this state here, this is the solid to, and vice versa, solid to liquid phase change. And right here, this is the liquid, liquid to gas to vapor. I'm sorry, I should probably say vapor. Solid to gas phase change. And so if you notice here, the temperature doesn't change. Now, typically the temperature changes because the heat is being added, and so the temperature increases because there's more heat flowing into the system, and it changes the temperature of the system. Here, heat is being added. Here, heat is being added. However, as heat being added, that heat is going into changing the structure of the molecule, structure of the compound, and so therefore there's no temperature change during that particular phase change. But during phase changes, there are no temperature changes. And remember, we were able to calculate for that because we were able to calculate. I'm sorry, for the phase changes, we were able to calculate for the heat involved in that using the specific heat here, the mass, and then here, then we had then the enthalpy. Sorry, the change in enthalpy for fusion, and this then was the change in enthalpy for vaporization. Okay, and so temperature changes are not considered when we talk about the phase changes here. And so why do I bring this up? Okay, if you notice here, the heat of fusion here for a solid to liquid transition. This is for ice, and by the way, this is for ice here. Okay, and so if you notice here, the heat of fusion here, that is the amount of heat needed. The amount of heat needed per mole of water, of ice, to melt it is about 6.1, and I want to highlight this for kilojoules per mole. Okay, take a look and compare that to the heat of vaporization, for water, and that's going to be 40.7 kilojoules per mole. Okay, it's almost more than 6 times greater. It takes almost 7 times more energy is needed to vaporize liquid water than it is to melt ice. Now, how could this, how does this relate to then what we were talking about? How does this show us then that the solid state and the liquid state are closer together in terms of their structure than the liquid and the gas state? Well, just imagine this. It doesn't take as much energy to disrupt the structure of ice because the structure of liquid water is fairly similar. Now, not fairly similar, I'm sorry, let me take that up, but it's similar enough where it doesn't take that much to disrupt that structure of the ice. Okay. However, the structure, and I put structures in quotes here for gas, for water vapor, is very different from that of liquid water. So you have to change it dramatically. Okay. And what accounts for that dramatic change in structure? Okay. And so how can we go about explaining why there's such a dramatic change in structure here and not so much here? Well, let's go ahead, let's take a look at that. Okay. We can determine, that's what we're going to examine here. And so that's what the purpose of this discussion is going to be, is to examine then why we have such a large amount of energy that's needed to change liquid to the gaseous state, but not so much for the solid to the liquid state. though energy is needed. Okay? The other thing is I want to point out to you then is that the densities here, we see then that these two states of solid and liquid state are much denser than the gaseous state, and they tend to be a little bit closer together than the liquid and the gases. Okay? And if you notice here with water, there is one key difference here, that is the density of water is greater than the density of solid. It's one of the few compounds. I think the only one that I can think of off the top of my head that actually does that. Okay? But the question then is this, okay? What is going on at the solid and liquid state? What's going on there that allows for the transition to be much easier than the transition from the liquid to the gaseous state? Well, the answer then lies in the intermolecular interactions that occur between the bonds. Okay? So let's differentiate between them what we refer to as intramolecular bonding or intramolecular interactions, as opposed to intermolecular interactions, which is what accounts for then the similarity in states between liquids and solids, and the difference in states between the liquids and the gases. Okay? So first of all, the intramolecular interactions, the interactions within a molecule, between the atoms within a molecule. So the other way we can put this is this is just a bonding, folks. When we refer to intramolecular interactions, we are referring to the bonding between atoms, within a molecule. So this is within the interactions within a molecule. So that's the intra part with it. Okay, so there it is what we have. And so if you take a look at each one of these molecules here, the intramolecular interaction is the bonding here. So we have a single bond here between the hydrogen and the oxygen. We have a double bond here between the carbon and the oxygen. We have a single bond here between the phosphorus and the chlorine. So these bonds, these single and double and triple bonds, these are the molecular interactions. Okay? And so that's what holds the molecule together. So that's what connects all the atoms in a single molecule. Okay, and so we can remember this by just remembering them that when we talk about intramolecular interactions, we are dealing with the bonds between atoms. So you want to make sure you keep that in mind as you move forward, because that will be different than from what we refer to as the intermolecular interactions, which is the interactions between two or more separate molecules. Okay, and so the intermolecular interactions here, and the key here in understanding this is that we're dealing with the prefix here, inter. That's the interactions between separate molecules, not within a molecule, not between the atoms within a molecule, but between the separate molecules themselves. And so there are three different types of intermolecular interactions, which we also refer to as intermolecular forces, and you'll see that term come up more often. So the intermolecular forces here, which is abbreviated IMFs, okay? There are three different types. Okay? We have the dipole-dipole interactions, of which the hydrogen bond is a type of dipole-dipole interaction that is unique, and so we actually assigned it a separate category as well, but it is a polar interaction. And then finally, then we have the London dispersion forces. Hopefully, folks, all three of these interactions sound familiar, that you have some recollection of what they are and how we can define them and how they work. But if you don't, I'm going to be quickly going over these with you as well. Okay? But do keep this in mind. The intramolecular interactions, that's the bonding between atoms, is much stronger than the intermolecular interactions here. Okay? Those bonds that holds atoms together are very strong. It's very difficult to break those bonds. We saw why. That's why we learned about that back in chapter 8, chapter 9. We talked about why when those atoms get together, we get an energy dip, and they are in a stable state. And so those bonds between atoms are very strong because they're stable. They're stable. However, the intermolecular forces here, they can be strong, but they are not as strong as the intramolecular interactions. Okay? So the intermolecular interactions, these intermolecular forces can be strong, but when compared to the intramolecular interactions, they are not as strong. So the intramolecular bonds are much stronger. Okay, they are much stronger than the intermolecular forces. Okay, so make sure you keep that in mind as we move forward with this. Okay, so With that said, then these bonds are between the molecules. Okay, so which one is stronger? We always expect then that intramolecular interactions will be stronger. How do we know that? We know that because we did the energy studies, and the enthalpy, the energy needed to break an intra bond is going to be much greater than the energy to separate out molecules in a particle. So just imagine this. If you can imagine this, the amount of heat needed to boil water, 100 degrees Celsius. Okay? The amount of heat to break the hydrogen-oxygen bond, many times larger than that. And we saw the OH bond, the amount of energy needed to break an OH bond in kilojoules per mole, and we can translate that into the amount of heat energy. We can calculate from the amount of heat energy that would be needed to break that OH bond. Okay, and so that's how we know about that. Okay, so let me just quickly go through with the little time that I have left here. And so let's talk about these different types of interactions. The dipole-dipole interactions have to involve molecules that are polar in nature. Okay? So you need to go back to chapter 8 and review that and understand how a molecule can be polar. But the polar molecules then, when they interact with one another, they interact through dipole interactions. And how does that happen? Well, the positive end of one end of the molecule, the positive side of one end of the molecule is going to be attracted to the negative end of the other negative end of the other particle. And so you'll have this interaction here between positive and negative poles that holds the compound together. Okay, so these interactions here will be the interactions between neighboring atoms. What they do then is that they are attracted to one another through the positive negative end, very much like two magnets coming together and holding that way. Okay, so these interactions are very much like ionic interactions, but remember the key difference here is with ions you have full charges. With these polar molecules, these are partial charges. Okay, so these dipole-dipole interactions will only occur with polar molecules. So you have to first establish whether the molecule is polar or not, and then what you'll do then is you can decide then whether it's a dipole or if it has dipole-dipole interactions or not. Okay, and so with dipole interactions, what will happen is molecules will arrange themselves that they will maximize the attraction and minimize the repulsion between neighboring molecules. Okay? And so with that said, then that's dipole-dipole interaction. Okay? All right, with hydrogen bonding then, hydrogen bonding is a special type of dipole-dipole interactions in that you have opposite charges attracting one another. Okay, so it is still a type of dipole-dipole interaction, but the interaction is much more specific. The interaction then is going to be between a partially positively charged hydrogen, partially positively charged hydrogen atom with a fully negative charge set of electrons. Okay, so you have then the partial positive charge here, and here on the anion, on the neighboring atom here, that's going to be partial negative. I'm sorry, full negative, because it's interacting with the electrons. Okay, so it's interacting with the electrons in the neighboring molecule. Okay, so what hydrogen bonding needs is a hydrogen atom, obviously. Okay, it needs also a lone pair of electrons on a neighboring molecule, and that lone pair of electrons has to be attached to a that hydrogen has to be attached to a highly electronegative atom. Okay, so let's take a look at an example of a hydrogen bond that can occur. Okay, so let's go ahead and take a look at this. So let's take a look at water here. Okay, so if we take a look at water, okay, let's take a look at water really quickly. Water obviously has a positive end. Okay, so positive end here is the hydrogen side, and what's left out here are the two lone pairs that an oxygen has. Okay, so what will happen then is the interaction between the lone pairs of one hydrogen molecule, of one water molecule with the hydrogen of another molecule, because remember the hydrogen atom here is going to be partially positive and the two electrons here are going to be full negative. The attraction between two opposite charges, that's a dipole interaction, but the dipole interaction here is specifically between a hydrogen atom and a pair of lone pair. Okay, and so like I said, the criteria that's required then is you have to have a hydrogen atom attached to a very electronegative atom, and that's what we have here. Oxygen is fairly electronegative. It's a couple of atoms away from fluorine. And then you have to have lone pairs as well, okay? And so if the molecule has all of those, then we can say then that that particular molecule can hydrogen bond with every other molecule around it. And the hydrogen bond, folks, is a very strong bond. It's a fairly strong bond, and it's a fairly widespread interaction as well. So the hydrogen bond, even though we refer to it as a bond, it is not technically, it is not a covalent bond. It is an interaction between the two molecules with the two separate molecules. Okay? All right. Let's continue on then, and let's take a look at what happens. So there it is. This gives you a better idea of blowing up for you the interaction here. This right here is your hydrogen bond. Okay, this is your hydrogen bond, the interaction between a partially positive hydrogen atom and a fully charged electron lone pairs here. So you need to have the lone pairs, you need to have a hydrogen atom, and that hydrogen atom must be attached to an electronegative atom. Those three criteria are needed in order for hydrogen bond to form. If any one of those are missing, no hydrogen bond will form. Okay, so let's take a look at what the effects are of hydrogen bonding, because hydrogen bonding is fairly important. Okay? So if you take a look at this here, you can see then that well, hydrogen bonding has a very important effect, okay, on the, for example, the boiling point. Okay? And so if you notice here in the category here where we have group 6A, okay, so you have oxygen here, sulfur, selenium, and tellurium. Obviously, water hydrogen bonds. Sulfur doesn't hydrogen bond as much. Sulfur is not quite as electronegative, so it doesn't. So if you notice here, as we go from tellurium to selenium to sulfur, okay, we get a huge jump in boiling point, because here we have hydrogen bonding occurring to a much greater extent. The question that I would be curious to ask you, and then let's take a look at the halogens here, folks. So we have all these halohalides here. Okay? So we have fluorine here, chlorine, bromine, and iodine. All of them should be capable of hydrogen bond, and they do to a certain extent, but not that to a certain extent. My question to you is this. And this is something that you can come by and ask me. I've seen it asked before, not quite in the way that I'm asking now, and that is, why then, if both of these hydrogen bond, why is the boiling point of hydrogen fluoride so much greater than hydrogen chloride? Okay? They both hydrogen bond. They both have they're capable of hydrogen bonding. What's the key difference there that causes that jump? Okay, so that's something you want to make sure you keep in mind. But do keep in mind here that just because an atom has hydrogen, just because a molecule has hydrogen atoms, does not mean it can hydrogen bond. Okay, so remember, what it also needs is to be attached to a very electronegative atom, and that electronegative atom must have lone pair electrons. Okay, all right. All right, so with that said, the last thing I want to talk about here real quickly is just the London dispersion forces. And the London dispersion forces are interactions that occur as a result of transient dipoles. The transient dipoles arise because electrons, remember, are in constant motion. So at any moment in time, you can have electrons gather on one end of the molecule, okay? And when it does, okay, that end of the molecule will be partially negative, the other end will be partially positive. At that moment in time, if it comes across another atom, another molecule, it will induce a dipole interaction between itself and the neighboring molecule. So you can imagine this. As the molecule A here establishes this instantaneous dipole, when it comes into contact with molecule B here, which has not done that yet, it will force molecule B here to send its electrons towards the left-hand side of that molecule so it can interact with this partial positive right here. This is what we refer to as a transient dipole, okay, dipole interaction, because it is a attraction between between a positive and a negative charge, but it's temporary. Transiency means then that it's a temporary dipole. If you have a temporary dipole, okay, you're going to have a temporary interaction, because at the very next moment, the electrons can shift over to here, and then therefore the electrons on this molecule B here will also shift to the other side to still maintain that interaction, but it's it's an interaction that remains in constant flux because the electrons are always in constant flux. Okay? And so that's what the London dispersion forces are. And so the London dispersion forces can account then for the interactions of particles, of molecules that are not polar in nature. They're not polar in nature, that have no hydrogen bonding, but they can still condense. They can still interact with one another. And so the evidence that we have then for these London dispersion forces is that particles, compounds that don't appear to have polarity, that they are nonpolar molecules, that have no hydrogen bonding can still interact with one another to form the liquid state. Okay, so the evidence for the London dispersion force is that we know then that all substances can eventually reach the liquid state. If you drop the temperature enough, they can exist at the liquid state. Even these noble gases, the noble gases, we can get them to get into the liquid state. Helium can be liquefied. You just got to drop the temperature quite a bit in order to get that done. Okay. All right, and so with that said, then these are some of the freezing points, and here we can actually solidify it here. So obviously you can tell then it's fairly low. Look, this freeze helium, we're getting real close to absolute zero. Remember, absolute zero is negative 273 degrees Celsius. We're getting real close. So if we can drop the temperature quite a bit, we can freeze these noble gases. And again, the solid state and the liquid state are highlighted by their interactions, by their attractions for one another. All of these atoms here, all of these atoms or all these noble gases cannot hydrogen bond. They don't have hydrogen in them. They cannot interact through dipole-dipole interaction because they are non-polar atoms. Okay? And so the only way that we can explain how these noble gases, these atoms can solidify is by saying that there are these London dispersion forces, that there are these interactions that holds these atoms together. Okay, and so with that said, then this is an example of I think we have an example of I think this is neon. No, let me just take a look at it real quick. Okay. Argon. So this is solid argon here. Okay, and so with that said, then the only way we can achieve this solid state is if argon particles can interact with one another through London dispersion forces. Okay? So if you come across a problem like this here, folks, and they ask you about this, how would you answer this? Which one is going to be? Which one's going to have the stronger intermolecular forces? Well, first of all, dipole interactions and hydrogen bonds tend to be stronger than London dispersion forces. But there's a huge caveat to that. There's a huge caveat you have to consider then, and that is the size of the molecule itself. The larger the molecule, the more electrons it has. The more electrons it has, the stronger the London dispersion force is going to be. Okay, so the London dispersion forces. Okay, so we'll call this the LDFs. The London dispersion forces will increase with increasing molecular size. And this will be apparent because with more atoms, the bigger the molecule, we have more electrons. The molecular size then means that we have more electrons. And with more electrons, the interacting with one another on both molecules, okay, the greater the LDF is going to be. Okay, so you have to be careful about this here, okay? And so if we were to generally categorize, hydrogen bond and dipole would be stronger than LDS. And so with that said, then we take a look at both of these here, and how you would answer this question is by listing, first of all, what type of interactions we have here. With nitrogen here, this is a nonpolar molecule. Okay, we know that. This has no hydrogen bond. There's no hydrogen. So the only interaction that it has then is the London dispersion forces. With water here, we have hydrogen bond, which I will refer to as H bond. Okay? It has also dipole-dipole interactions because it is a polar molecule. But because water also has electrons, obviously, it also has London dispersion forces. And what I told you folks before, and we talked about this if you had me, if they ask you what type of interactions are present with any particle, okay, you can always say London dispersion forces, and you will get points for that because every particle, every molecule has electrons, so therefore they must interact through London dispersion forces. And so which one of these will have the stronger interactions? Well, obviously water here, because water then has all three of those, as opposed to nitrogen, only one. And so water then has the stronger interactions between them. So we can expect then water to have a higher boiling point than liquid nitrogen. We should expect it to have a higher melting point than liquid nitrogen, and it does. Okay, so those are some of the things that we can confirm about our answer here. Okay, that's the evidence that we can use to suggest then that water has stronger intermolecular forces than nitrogen. Okay? All right. Another way they can ask this question of you here is that if you take a look at these two here, okay, and they give you these are what are called isomers of one another. Isomers are compounds that have the same structure, the same atoms, okay, as the other, but they are connected in slightly different ways. Okay? So when we take a look at these two isomers here, one is for ethanol on the left here, so this is going to be ethanol on the left. Okay, so this is ethanol here. Okay, this is dimethyl ether. Okay, and so with these two isomers here, what can we say about their boiling points? Now remember, the molecule with the greater number of interactions will be held together. The separate molecules will be held together more tightly, and so therefore it will take more heat to break those interactions. So if you have more interactions, it's going to take more heat to break it. It means then they'll have higher boiling points higher boiling points as well. Okay, so let's go ahead and list what we have here. Okay, so if we take a look at this molecule here, obviously we're going to have both molecules will have LDF. So make sure you just write that down. Both of them will have London dispersion forces going for them. Okay, all right. Now, if you were to draw this structure here, okay, this one also has, this end is polar. Just imagine this looks like water, where this end here, this part here is replaces one of the hydrogen atoms. So obviously this then will be polar as well, so it will have dipole interactions. We don't have that happening here. Okay? We don't have that happening here, and these molecules tend to be a little bit bulkier as well. So we don't have dipole interactions here. Okay? We do have a dipole interaction occurring here. Okay? And then finally then, if you take a look at this, this then would have hydrogen bonding, because there you have a hydrogen attached to an electronegative atom with lone pair electrons. So you would have then H bonding here as well. Okay. And you don't have that here. So even though this molecule does have hydrogens, the hydrogens are not attached to the oxygen. Remember, the hydrogen has to be attached to the electronegative atom, which it is not here. And so this does not have hydrogen bonding as well. So of these two then, which one would be more difficult to separate out the molecules? Ethanol would here. And so if that's the case, then ethanol then would have the higher boiling point of the two molecules presented to you here. Okay? All right. With that said, then what I'd like you to do is take a look at this last one here. And I'm not going to ask you to submit it, but this will give you more practice. Okay? This is a question that I did take from an AP exam in the past, and that is, which one of these will behave more like an ideal gas? Now remember, the key to understanding this question then is they're asking you about the ideal gas, and ideal gases have no interaction. The assumption we make about ideal gases is that they have no interaction. And so the question then is, of these two gases, of these two real gases, which one would approach the ideal state more than the other one? Okay? And the way that you can answer this question is the reverse of how we answered the previous two. The previous two, the more intermolecular interactions that a molecule has, the stronger the interactions. Okay? Here you want to identify the molecule which has the least amount of intermolecular forces, because if that's the case, then it has less interaction. Okay? The interactions will be weaker, and therefore the gas then will behave more like an ideal gas. Okay, and so the answer here, and please come up with the make sure that you can understand that the answer here is nitrogen. Carbon monoxide, CO, has London dispersion forces. So let me just go ahead and finish up here. I've gone a little bit over time anyway, so let me just finish up here. Okay. London, both of these have LDF, so we've already agreed on that. Everything has London dispersion forces. Neither one of these have hydrogen bond. They don't have hydrogens. However, this is a polar molecule, and so therefore this will also have dipole interactions. And so therefore there are two interactions holding carbon monoxide particles together, only one for nitrogen. Okay? So there's less interactions with the nitrogen particles, and so therefore they will behave more like an ideal gas, okay? Because they have less attractions from one another. You have a lot of attractions here. You got two compared to one. Okay, and so with that said, then if you think about it, then we have two particles that are almost identical to one another. Both of their molecular weights are about 28 grams per mole, and they both have 14 electrons. And so the key difference here then is that it's what's holding the separate molecules together. You have more interactions holding the carbon monoxide together. Okay, so there are more interactions, so it will behave less ideally than the nitrogen itself. And again, the operative term here is ideal. Okay? An ideal gas with an ideal gas, remember, we're assuming that there are no attractions between the particles. Okay? The nitrogen comes closest to that because it only has one. Okay? All right, folks. So that's it. And I know I went over a little bit here. I will be available tomorrow. Okay, during class time, I will be available tomorrow. So stop on by. I'll have the Zoom open and ready to go. So if you have any, I'm sorry, tomorrow. Um, if you have any questions, please come by after school. Sorry, I already, because of what I've told you, I already made plans to meet. I had a meeting tomorrow, so I apologize. So if you have any questions tomorrow, come by Zoom, okay, after school, 1:30 to 2:30. But we will not meet for class. You won't have any lecture on Wednesday, but please check in though. So I'll have the attendance posted. Please check in and then go relax for the 40 minutes of our class time and put chemistry behind you. Okay. Good luck on Thursday. You'll do fine. You guys will do fine. And then I will meet back with you. We will meet on Friday during our regularly scheduled class period. You can let me know how things go, and then we can talk then. Okay. All right. So until then, good luck, folks. If I don't see you tomorrow, relax. Forget about chemistry for a little while. Do your best under this given circumstances. That's all that anyone can ask for you, and then set it aside and move forward and not worry about it. Okay. All right, folks. Well, good luck to you on the AP exam, and I will see you either tomorrow or on Friday. Okay. Have a good afternoon.